Due to tonight's introduction, Paul Withey is currently Professor of Casting Technology at the University of Birmingham. He has been working in the field of casting with a specialism in single crystal casting for 3 decades. The majority of his time was as a casting specialist at Rolls-Royce Aerospace, primarily focused on turbine components. Another talk there. Prior to this, Paul worked in research on fracture mechanics, where he developed his interest in the DeHavilland Comet, and that's his special subject for tonight. Ladies and gentlemen, Paul Withey.
Okay, thank you very much. Normal accusations are that I speak too quickly, and hopefully you can all hear me. If you can't, wave your hands. For those of you that can't hear me in the back. Happy for this to be video, so that's good. And for those of you that are in the wrong place, this is about to talk about the DeHavilland Comet, which is, when it was designed, was an absolutely beautiful aircraft. And the shock of that aircraft when it rolled out of the hangar in the late 1940s was immense to the aviation industry, something that we don't kind of quite see the benefit of today. But I'm going to go through. It's been the subject of many documentaries. There's a reasonably short list, but there's many more, and YouTube videos. Yes. So what comes to mind about these? Go on, anybody.
Square windows.
Square windows. So we'll discuss window shape and a number of other things. So we'll go through that. Just to kind of disabuse you of square windows straight away, that's the shape of the DeHavilland Comet window there in red, to scale with the Boeing 70, the early first series 707 for one airline only, and then 707, 727, 737. Boeing got quite good at that shape of window. Boeing 777 made them a bit bigger, as did the Dash 8, 747, and Boeing 787, of course, it's made out of plastic. So actually they can have windows any shape we want. But the window radius at the corners of the DeHavilland Comet and the early Boeings was 3 inches. Same shape. There you go. So, square windows. That must be the reason that this one fell out of the sky and none of those have. You know, because that was nearly square and they're rectangular. I'll let somebody else work out the stressing on that. What I'm looking to do. Bit of the background, general and legislative background to the DeHavilland Comet at the time. Because there's a lot of criticism about what DeHavilland should and shouldn't have known. I'm going to go through that. But also, what did the regulator think? What did the regulator know? What did DeHavilland know? What did science know? The Comet itself, the accidents. I'm going to go through the RA investigation briefly and cover the things, cover a fraction of the things that they did. Because they did a really, really big investigation. It comes to about that thick in paper alone. Some subsequent work that I've undertaken, a bit of a model analysis, and basically take you through some of the understanding of where I think we are today. A little bit of an Easter egg at the end for those of you. Right, general. Post-war air travel was dominated by large propeller-driven aircraft. That was, where we were. The US industry had developed aircraft that were used for military transport that could actually go straight into operation in civilian fields. They focused on that. They needed to move troops across the Atlantic, they needed to move troops around the world, across the Pacific. The UK didn't tend to make too many transports. We were too busy taking aircraft like we've got knocking around here and dropping bombs on other people. So we didn't think about moving vast quantities of people by air. And so when we came out of the war, we got the Avro York, which was an airframe. Wouldn't it be a great idea to stick lots and lots of passengers on it? It wasn't designed for passengers, really, not the greatest of ways forward. And so, as air travel was becoming more and more popular in the post-war period, the US industry had really stolen a march. It had got some nice airframes, it had got long range, it could turn those airframes into reasonably comfortable passenger experience. And a lot of airlines were selling the passenger experience. Military aircraft had been using gas turbine power plants since 1942, but they were to preserve only a few air forces at the time. They have a good pedigree in military jet aircraft. The Vampire was the second jet fighter to enter service with the RAF in 1945, and it was powered by one DeHavilland Godling engine of about £35,000 thrust at the time, in old money. Gloucester Meteor was the first aircraft to enter service. Does anybody know which engine powered the first Gloucester Meteor that flew?
Rover.
The Rover made the prototypes. The Welland was the Rolls-Royce engine that kind of fitted it in. This is going online, so I couldn't possibly comment about whether Rolls-Royce are going to be late on another engine project. But the Welland was late, and it actually first flew. Prototype number 5 was the first to fly, and that was the Goblin engine. So the DeHavilland Goblin engine actually powered the Meteor first, before the Welland came along. There you go. But the Brabazon Committee during the war realised that this was going to be the case, so take a step back a few years, and they decided that in 1942, right in the midst of the war, that they needed to be thinking about what was the situation at the end of the war. And some of this impetus was given when Winston Churchill took a trip to Russia in a military stripped-down consolidated Liberator and decided that the UK needed some passenger aircraft by the time he came out of the war, because he wasn't going to sit in that aircraft again for any distance. And so the impetus was given by a very, very uncomfortable flight for the Prime Minister. And so he decided that we needed to have this committee that came together and decided what we were going to be flying in the future. And they came up with a number of different types. I wouldn't say it was definitely special interest, but everybody came together and decided what aircraft the UK needed. And different different aircraft manufacturers said, we think you'll need one of these. Please allow us to go and develop this during the wars, because if you could put a bid into one of these different types, you were already on the side of being in favour with the government because you were developing an aircraft, as they said. So the committee then came out with a load of these aircraft, but things like Geoffrey de Havilland wanted a Type 4. There's all, de Havilland was seen as a replacement in here. There's other aircraft manufacturers were chipping in, saying, we think we can make one of these. We think the industry really needs one. So it was a bit backwards, but that's the way it went. And Type 4 is where we came out. Jet-powered 100-seat transport. Didn't quite meet all the requirements, but it certainly started us off. And it was described as a high-speed mail plane. The idea being that one thing that the Empire would need after the war is some way of communicating around the Empire. And so a high-speed mail plane to get the post to the various outposts of the Empire was what was being looked at. Key features as part of the design that de Havilland went into: aluminium construction. That was a given. Hydraulic actuation of the control surfaces. Now that was going to be a first. The DeHavilland Comet was the first passenger aircraft with hydraulic actuation of the power surfaces. By the way, one of the people that I chatted to about that was John Cunningham, who was chief test pilot on the programme. And he said lots of pilots at the time were going around going, "Oh, you'll lose feel of your control surfaces if they're not connected by cables." Which he found quite interesting, because at that point there was all the debate about Airbus fly-by-wire, with pilots going, "Oh, if it's not connected by hydraulics, you'll lose feel." So just wait for fly-by-light, when the pilots are going, "Oh, it's not connected by anything electronic." Anyway, I can see it going around that one again. But John Cunningham did say that hydraulics were going to come in, and it was going to upset a few of the older pilots, because no longer they've got big pieces of cable to all of the control surfaces. 4 independent hydraulic systems just to make sure it was safe. 4 de Havilland Ghost engines. Nearly 5,000 pound thrust, 36 passengers, range 1,750 miles. Which is why, if you look at all the routings that the de Havilland Comet did, it was always, Heathrow. First stop, Rome. Doesn't matter where you were going in the world, first stop was Rome. Land, refuel, have a cup of tea, get back on, then fly on. Cairo. And you hopped around the world in 2-hour stages, because that's your length. That's where you were. And they hopped around the globe like that. Cruising speed, nearly 500 miles an hour. Cruising altitude, 35,000 feet. And weight, 50 tons, give or take. A lot of innovation in that. Today we look at it and go, that's easy. That's not even novel. Yes, it was novel at the time. And this was groundbreaking. And the crucial things were, that's where you looked at the passengers, 36 passengers. Constellation, piston powered, 60 to 81 passengers. Connie, 4,000 miles, but much slower, lower altitude, but still pressurised, and nowhere near the weight. So it was comparable, except for the number of passengers, to a piston aircraft, but it went much quicker. As a bit of an aside, Frank Whittle, when he first started working on gas turbines, put out this graph, which kind of is a bit confusing, but it looks at a propeller-engined aircraft all the way through to jets at different speeds, and I've put in the Comet, which data he didn't have, But you can see how the faster the piston engine aircraft goes, the more and more is taken up with power plants and fuel to the point where you don't have an economic range or an economic payload. Whereas jets actually hold this a lot longer, at higher speed. Frank Whittle knew this, that's why he pushed for the gas turbine. The DeHavilland Comet, slightly off from Frank's calculations, but that's why everything had to be stripped down, because the whole flying experience you needed to fly with passengers, so everything had to be as light as possible, because the payload wasn't great. Gas turbines are more efficient at high altitude, which is why they picked them, so the passengers would need oxygen. They decided they'd go for a passenger cabin rather than giving everybody a little mask that dropped down and you plugged yourself in at the start of the flight, which they could have decided to do. You know, all options were available at the time. We're just used to being able to walk around the cabin. And they picked 8,000 feet as the optimum altitude. So that people didn't suffer from lack of oxygen, but it reduced the pressure differential between the outside and the inside of the operations. So that was where we ended up. 8,000 feet has been pretty standard until the Boeing Dreamliner. So the numbers that DeHavilland picked became industry standards until the Dreamliner changed the game with the polymer matrix composite fuselages. Aluminium airframe to make it as light as possible. Fuel consumption, by the way, on the engines. Thrust to weight ratio was terrible. It drank fuel, but it was the first generation of gas turbines, which is why they needed to run everything as light as possible, because they needed to put in as much fuel to actually get the passengers to where they were going. Airframe was basically stripped down and as much as it could be. And to do that, they decided that riveting was going to be expensive and heavy. So for the bulk of it, they used what was called redux, which was developed out at Duxford, to glue the aluminium alloy together. The aluminium alloy is out of service now, and I'll come back to that later. But they used this aluminium gluing technology, which they first trialled on the Dove, which entered service in 1946, and the Dragon Rapide. They basically used this aircraft to trial a load of stuff around. It was a much easier aircraft to fly and to design and work with, because it was piston engine. But they actually were able to use an all-metal body and use redux to actually, and they practiced on other airframes, so they knew what they were doing in that sense. And it was developed by Duxford, as I said. A liquid phenolic resin and a polyvinyl formal thermoplastic powder, stuck it all together, reacted it. It's been used in all sorts of different other applications, clutch plates, for example. And it was used to join ribs and stringers to the aluminium skin of the aircraft, as well as doubler plates and other bits and pieces in the wing. So they've got lots of experience of this, like to use it. And it's been used on a number of different aircraft, and that's just a reasonable list of the ones that somebody's picked up and run with. So Saab's, the Trident, various aircraft have used it over the years. So it wasn't unknown technology, and they tried to use it as much as they could. But there were certain areas where they could not get jigs and fixtures to do the reduxing. Around the cutouts, the windows, the door frames, etc. That was one of the areas where they couldn't do that. So they said, well, that's all right, we'll go back to riveting. So they went all the way back and said, we'll rivet where we can't redux. And that was a decision. It was a cost decision. You know, they could have made the fixtures, it would have been too expensive. So they decided that they would just rivet around the windows and doors, and other places where they just needed it. And going back to the 1940s, you know, Steel magazine in 1940 reported this, you know, in as much as the average plane requires around 45,000 rivets, much attention is being paid to automatic riveting. This was in the middle of the war when people were churning out lots of aircraft. Vultee, one of the companies, installed an automatic riveter which punches the hole, inserts the rivets and heads the rivet in one operation, doubling the output per man. Several aircraft companies are purchasing similar machines. DeHavilland had some of these for their works. And there were the Erco machines would basically take two sheets of aluminium, slap them together, punch through a hole, pop the rivet through, dimple the top layer, pop the rivet through, head the rivet, jobs are good. Now, to get it as light as possible, they used 22 gauge skin, 0.71 millimetres. If anybody wants to see what that is, that's a piece of DeHavilland Comet skin. 22 gauge. This is, I'll pass it around. What I'm going to pass around, it's a piece of DeHavilland. It's got a few burrs on it, it's not in great shape. Don't impale it in the head of your friend next door, you know, just be careful. They did actually thicken up the skin around the wings, 20 gauge, went to nearly a millimetre, so they actually ran it a millimetre-ish around the windows. And the UTS of the alloy, the ultimate tensile strength, about 450 megapascals. So it's a reasonable aluminium alloy. It's 2000 series alloy, nearly. So it's comparable to what would be seen as an aerospace alloy today. Maybe slightly worse properties, but not by a huge amount. DeHavilland did estimate, and they've come in for a lot of criticism for their estimates, that the stresses around the windows would reach 190 megapascals over a broad area near the cutouts. And there was a lot of debate after the accidents about what over a broad area meant and what the spot figure might be and how close that might get to the 450 megapascals. So, yeah, we'll see. Right, fatigue. Metals will break under a load which is repeatedly applied and then removed, though they can support a much larger steady load without distress, is the definition at the time. So you can take a repeated load, you have to be much lower to actually get it to survive. It had been known about for 100 years, roughly, by the 1950s. We knew that it existed. We found it on railway axles in the 1800s. And military aircraft had suffered fatigue during World War II, especially in wing structures. And there was a programme of examination of wing structures during the war because we had fatigue. The only reason it wasn't a major problem during the war was that aircraft didn't tend to last that long. So your evidence got taken out of service one way or another. So it wasn't seen as too much of a problem. DeHavilland knew about fatigue. They knew it existed and they wanted to take steps to prevent it. But there was no real scientific understanding of fatigue beyond the fact that it existed. British civil aviation requirements in 1949 were that you did a proof pressure of the cabin to 1 1/3 of the pressure that you're going to pressurise to, with no permanent deformation. So you work out what your pressure is at 8,000 feet compared to a 35,000 feet flying altitude, about 8.25 psi, and you basically say it's got to be able to take that, and the design pressure is twice that pressure. DeHavilland then said, that's all right, but what we'll do is we'll do a 2p proof pressure and design to 2.5 that pressure. 2.5 times that pressure. So actually they were more conservative than the regulator. They actually came out and said that feels more comfortable to us. And they shared the belief with the regulator at the time that actually doing this would mitigate against fatigue. And that was just operating in that way would satisfy not just the regulations but make them immune to any kind of fatigue failure. That's what they thought. But people kind of knew about fatigue thresholds, so minimum stresses below which you don't get fatigue. They thought it didn't apply in aluminium, but we weren't quite sure at the time. Not enough evidence to go either way. And so you just over-design. Now, if you're a civil engineer and you over-design, that's fine, you can just build a bigger foundation. But because they had to fly the plane, over-designing meant more fuel, so it's a fine balance between over-design and actually having a passenger to take. And that was the balance that DeHavilland tried to strike. Hence the fact that the skin is so thin. Draft requirements that weren't out at the time, but in 1952 when the aircraft was certified, were still draft. Static test to twice that proof pressure. Proof test it to 1 1/3. 15,000 applications of 1 1/4 times that. There are all sorts of things going on. Structural parts needed to withstand 3 times the pressure. So doors, riveted joints, window frames, you have to do 3 times the pressure. And they thought that 15,000 cycles was seen as the lifetime of the airframe. For those of us that have talked about aircraft doing 100,000 cycles these days, we've kind of pushed that out and out and out. So we've kind of learned along the way. And they felt that this 1 1/4 application of the application of this proof pressure would cover the scatter in fatigue results, because they were very much aware that you do one fatigue sample and you get a different result, maybe to a factor of 1 to 9 in lives. Because we didn't understand it, we had this kind of scatter. So we had to kind of take that into account somehow. And it wasn't well enough understood. It was something that happened. Neville Shute, in his book No Highway, focused on this kind of almost unknown creation to create his novel No Highway. Interestingly, he worked at DeHavilland as well, so he picked up this worry bead about fatigue. DeHavilland took 2 cabin sections. Forward section, the front 26 feet, and the middle section over the wings of 24 feet. They took them, they stuck them inside effectively a chamber, a water chamber, but an enclosed kind of almost like a diving pod, and they pressurised to 2p, and then they cycled up to 18,000 times in the front section and 16,000 times in the midsection, which exceeded just about every kind of requirement that were being given to them. And in fact, when they went into service, I think the front section had done about 16,000 cycles at that point, and so they felt that they got a bit of leeway before the fleet actually caught up with them, because they were continuing to run these things on, and they hadn't seen fatigue. So they'd exceeded everything they thought, and the comets were catching them slowly. Sections including the cutouts of proof tested to stresses higher than 2B. So they really, threw the kitchen sink at all of these bits just to see what happened. It wasn't like they just kind of chucked it up there and hoped that it would stick. They really did try to stay ahead of the game, understand the requirements and stay ahead of them. So the Comet was rolled out in 1949, so much to the shock of the press. First flight, 27th of July 1949. Story about that. John Cunningham, who did that flight, did admit afterwards that he was not flavour of the month with the aviation press for probably the rest of his life. Because they rolled it out of the hangar, and the press came out, took all their photos, and John did some kind of taxiing trials up and down the runway at Hatfield. Got to about 6 o'clock at night. Everybody had kind of got very happy, gone home, went off to Boots to develop their films or whatever the journalists did. And John thought, it feels quite good. Let's see what happens if we push it up a bit. And he took off. So the first flight was missed by all but one journalist. And all the others never forgave him for the fact that the first flight of a jet-powered civil airliner was completely missed by the press because John did it about 6 o'clock in the evening just because he felt like it. But having met John, that feels it in character. Anyway, lovely aircraft entered service 1952, London to Joburg, and I'm going to pass this around. This is the 1952 sales brochure for the DeHavilland Comet. So if you fancy having a quick shufty through that, that's the sales brochure, I'll pass it around. And just like the one that used to be here, if you look at the cutaway at the back, it's really nice, and there's male and ladies and gents toilets at the back. You see, I don't know how you cope with, very nicely done anyway. Inaugurated the London to Tokyo service, did a Joburg service first, then London to Tokyo. 1.5 days to Tokyo, which today, it's 13 hours-ish. 1.5 days to Tokyo, but that half the journey time. So load factors, nearly 90% load factors in that first year, because everybody suddenly decided that was taking days out of their journey time. And it put the UK industry at the forefront of the field. That just shows the route map. As I said, everywhere had to go via road, and that's at Heathrow, just for the 2 hours. And then it kind of split up, and it was always in 2-hour segments. This shows you some of the elapsed times, 21 hours, 20 hours, 25, 36. But in 1 year into service, 370 hours per week, nearly 150,000 miles, and 20,000 unduplicated miles. It was really ratcheting this up. It had never, at that point, held records for point-to-point between various airports because of the jet aircraft flying. Number of accidents. Rome, 26th of October 1952, Yo Zebra, damage beyond repair on takeoff, nose too high during the takeoff's roll. Karachi, 3rd of March 1953, this was particularly a tragic one. That first one, John Cunningham spent a lot of time working with the pilots on that one. And it turns out that if you're a pilot converting from a propeller aircraft and you go to jets, when you're flying propeller aircraft, you kind of get used to the fact that the prop wash will give you lift off the wings. So you get to a point where you know you can take off, you just pull back on the stick, the prop wash gives you lift, and the plane takes off. The jet technology did not give you that prop wash over the wings. So what happened was that the pilot if you pull back too soon, the wings tipped up, they stalled, and the plane wasn't taking off at all. It just ran down the runway. And the Rome accident was exactly that. John worked with the pilots that were learning this new technology and developed the method of saying that you get V1 for decision speed, you get a rotate speed that's faster than that. So VR was defined by John Cunningham as a speed at which you could actually rotate without stalling the wings. And this was new to this technology. The problem was, despite the fact that one of his friends who he taught in that Karachi accident, unfortunately, they were going for the fastest journey time round to Canada in a Canadian plane, and he was just tired. It was early in the morning, these horizons were probably out, and he just forgot pulled back, never took off, ploughed into a structure at the end of the runway, killing all on board. So the Comet kind of had a few stalls there. The Calcutta one, you get the conspiracy theory saying this was possibly fatigue. I've been through a lot of the photos, so I can't see that. It flew through a tropical storm flying out of Calcutta. Really violent storm, probably ripped the tail off, at which point the rest of the plane didn't fly too well. And the tailplane did break away. I can't see any evidence of fatigue on any of the photos, although there's none of the extra aircraft still left to examine. So we had a bit of a checkered history. And then, Yoke Peter, the aircraft that made that inaugural flight on the 10th of January 1954 just crashed into the sea. Eyewitness accounts said there was flames coming from part of it, but it broke up at high altitude, crashed into the sea. All the Comets were grounded. An investigation was started. Arnold Hall admitted that the construction of Yoke Peter started from that first accident and not later on, because the Royal Aircraft Establishment at the time was helping out with major investigations by taking bits, reconstructing them in a hangar, seeing what they could do. So Yoke Peter's construction started in January. But the committee that met said, well, what could have possibly gone wrong? Could it have been an engine failure? Well, let's strengthen up, and they put extra strengthening around the engines just in case it was a turbine disc failure that had popped out and brought the plane down. They looked at all sorts of different things, overpressurization and refueling, did lots, but there was no real information from the accident itself that said what had happened. Plane had broken up at altitude, caught fire, crashed into the sea, got to the bottom. And Lord Brabazon, who chaired it, said, we've looked at just about everything, we've done everything we can think of, we're going to let the plane take off again. So, flight services resumed on the 23rd of March 1954. Near Naples, 8th of April 1954. Yoke. This photo, the gentleman showed it to me after a talk, was taken by his father on that morning. It's probably the last photo of Yoke. Unless anybody knows differently, this is probably one of the last photos of Yoke. It was on the ground being refueled, rekitted before it took off for that flight. Crashed into the sea. Identical circumstances, it appeared. All Comet services were suspended by BOAC, and the certificate of airworthiness was withdrawn later on that month. So effectively it was grounded. The Ministry of Supply instructed Sir Arnold Hall, the Director of the Royal Aircraft Establishment, to undertake a complete investigation of the whole problem presented by the accident and to use all of the resources at the disposal of the establishment. So basically you're doing nothing else but this. And Sir Arnold turned the entire establishment over to look into the accident. The Royal Navy was brought in to actually see what could be brought up from the bottom. The Elba Comet, the second one, crashed. It's still down there. It was in too deep a water to actually stand any chance of getting it back up. But the Royal Navy worked hard on Yoke Peter. They used all sorts of methods to try and get it up. It was the first use of effectively TV-controlled kind of submersibles to try and pull some of this stuff off the seabed. And they a few months with trawlers, with the Royal Navy, just trying to get as much back up as they could. But the Royal Aircraft Establishment itself did a number of different things. That's the list of them that they went through. They did not know what they were looking for. Just like the previous investigation, they had no clues as to what could have caused this. So they were doing a rebuild of the Comet, fatigue tests on the pressure cabin, on the wings, on the tailplane, static strength, damage to the outer wings during refuel. It was high pressure refueling for the first time. Could that have expanded the fuel tanks? Could they have exploded because of that? There was all sorts of questions because of the design. Loss of control because it was hydraulics. They were doing free flight dynamic tests and miscellaneous investigations, and finally medical aspects of the accident. One of the few things they did manage to pick up, apart from a few seat cushions, was bodies. And so medical investigation into the deaths. What I'm going to focus on today really is just those top two, because actually those were the two where the answer came from. But at the time, the Royal Aircraft Establishment did not know that. They just kind of threw the kitchen sink at everything. And the final report covers all of these aspects. So, fatigue tests on the pressure cabin and wings, full cabin fatigue tests. They decided to use water to prevent explosive decompression, just like DeHavilland had used, because actually you don't want to kind of pressurise it with air and then blow it up with the force of a 500-pound bomb, which is what it would have been like if they'd have actually used air. And then it meant they could preserve it. 2 water tanks were built, taking 218,000 gallons, They needed 2 water tanks, one at the top because they needed to store the water when they drained it down to do the inspections. And that was because Sir Hall said it was quite difficult negotiating with the water company to actually have that much water, because he wanted to pinch that much water out of the water supply that was clean, because he didn't want nasty things growing in his planes, and actually swap it out. So he couldn't just send it back to drain. That wouldn't have gone down well. So he actually had 2 tanks made and he pumped between the 2. Simulated flight cycles using hydraulic rams, aerodynamic loads using hydraulic rams as well, and a 2-hour flight simulated in 5 minutes, and that was the plan. That shows how it came out. They flew comets with strain gauges and looked at the stresses that were imposed on airframes, and they mapped them and said what they looked like, and then they tried to replicate that using water pressure and hydraulic rams. And Uncle, one of the BOAC aircraft, they stripped out all the seats, they put it inside, they put some weights in to replicate a flying load, and they stuck the wings out of the side through rubber, and they started to pressurise it. These are completed 10 passenger flights with DeHavilland plus just over 1,000 pressurised flights in service, and a number of other unpressurised flights as well as part of its proving runs. Now, everybody says, oh yes, it did another 1,800 cycles before it failed. That took quite a while to actually occur, because actually they were doing 2P proof tests every so often, so they'd drain it down, they'd inspect it, they'd pump the water out, dry it out, go in, test it. It was taking them months. This happened sometime during the summer when it actually failed. It wasn't a kind of quick, oh, we've just done this, it's been a couple of days. Apparently the guy who was sleeping on a camp bed in the hydraulics room woke Sir Arnold up at about 3 o'clock in the morning saying, it's just failed. Everybody was quite surprised it had failed so soon, but it was in the middle of the night. Number of flight cycles that it had undertaken at the time of 3,057. So that was a failure. But they had actually been mapping all of these. They pulled this airframe in, they found other cracks, and they were monitoring them. And it just so happened it fell off that one. Well, thank you very much. Thanks. Test history just goes in to show that. They tested it, they kept inspecting it, they kept running it. And if they found a crack that got particularly long, they'd kind of stop it, either drill stop at the end or put a rivet over the top of it and take it away and then carry on testing. So they actually used it for a number of different inspections, a number of different cracks, and they were just chasing them through. They also did stress measurements around the cutouts, and they found that unlike the 180 megapascals that DeHavilland reckoned, it got up to about 297 megapascals, which is getting fairly close to the 450 megapascal UTS of the alloy itself. So it was getting pretty marginal on the strength of the material. Peak stress, as I said, 70% of the peak stress. But they mapped it around all the way around cutouts, they put strain gauges in, they looked at all the different positions, mapped it out to make sure they understood what the stress field was like around the windows. So unlike DeHavilland's, it'll be about 180 megapascals in the general area of a cutout. They actually did point measurements and found out that it was much higher. But DeHavilland, to give them their due, they believe that they'd made a general assumption and then tested it to pieces. And if, rather than making a precise assumption and not doing much testing, they'd done it the other way around. They made a general assumption, designed on it, and then tested it to failure to see what happened. So they thought it was safe, because if it didn't fail in test, then it wasn't going to fail in service. And that's where they were caught out. Rebuild of Yoke-Peter. Royal Navy managed to get as much of the wreckage as they could. 70% of the aircraft was located by September 54. Yoke was never coming back up from those depths. And flight profile was similar, so they reckon that Yoke-Peter and Yoke suffered similar failures, and the forensic evidence was similar. And the interesting point about that, when you come to the end of it, Yoke was the first aircraft accident where it was forensic evidence on the bodies that gave the definitive accident cause. Because there were the same modes of damage to the bodies in Yoke-Peter and Yoke. There was explosive decompression and lots of people got bashed about by cabin bits. And they were able to say, well, if it's the same for both of those, it's probably the same mode of failure. So actually, Yoke's cause of failure was seen to be fatigue, although we've never actually got evidence to prove it. tail frame seemed to separate early in the sequence, but there was damage from coin impact and, to an extent, the internals of the cabin. So you can see score marks, there's a coin indent, and there's a piece of the carpet stuck in the leading edge of the tailplane. That obviously came out of the cabin before the tailplane broke away, so some kind of sequence was being built up based on the damage that they were finding. And score marks across cracks, those cracks couldn't have occurred and the score marks be continuous across them. So there's all sorts of things happening. They built it up on frames. It's one of the first accidents where people actually started to build it up on frames and try to get back to that key piece. The actual key portion of the cabin that kind of broke the investigation was found trawled off the bottom in August 1954, cleaned and sent back to the Royal Aircraft Establishment. And they found a number of things when they inspected it. Manufacturing cracks were found in a lot of pieces. And actually the DeHavilland specification said if you see a crack during manufacturing, you stop it with a 1/16 of an inch 1.6 mil drill. So if you see a crack, drill through the end and it'll be fine. Now some of those cracks stopped and didn't go any further, some didn't and the cracks grew on. There's one that didn't quite work. They obviously saw it, stopped it and the crack ran on. So some of them during these were seen to continue. So lots of cracks were seen coming out of rivet holes. Some of them were picked up during manufacture and inspection, some weren't. What they did though find out was they worked out the breakup sequence, so that's the kind of the report. They knew that the first thing to happen was the top of the cabin split open down, the top line broke apart and the two halves flew out. They knew that was pretty early on because they found some of the white cheat line from the Comet scraped across the wing surface before the wings broke. So they know that the wings then broke after the cabin had come out. They knew the tailplane came off after the internals of the cabin had come out, for example. And then the nose, tail both broke off, the wings split up, and that broke the integrity of the fuel tanks and they caught fire. So they worked out the sequence. They got it all the way back to one piece, just behind the aerial direction finding window, the rear aerial direction finding window, which were effectively slightly larger cutouts, just like windows. But that was for the avionics rather than for passengers, and it came out of the back of there. And when they looked at it, they could see that there was a bolt hole. The crack grew either out of both sides of the bolt hole, with evidence of fatigue going both ways. The crack grew to its critical length, and the cabin burst open. Now, could be argued that should have been picked up on service, but this was underneath a doubler plate that was around the window. So to actually find it on a very young aircraft, you'd have had to strip all the paint off, take off the doubler plate from being on top, and then go in, and that was never going to happen, not at that age of aircraft. So this was highly unlikely to be picked up. That's from the actual report, those photos. And so we end up with the RAE opinion that says we're pretty certain that it's all due to fatigue, and that's just the wordage of it in accident note 270, basically saying that it's definitely fatigue, it's come from a bolt or a rivet hole, and it's grown to a critical length, and it's popped the fuselage when it's reached the critical length, and the stress has forced it through. And that because there's no wreckage from Naples, it's probably exactly the same cause due to forensic evidence. Now that was picked up by the Court of Inquiry, that became the standard response, that what actually, the official line on what caused it. And they produced a lot of documentation to prove it. And the Court of Inquiry, as I said, agreed with the RAE findings. Crash of yoke Peter was caused by fatigue failure of the pressure cabin. Similarities between yoke Peter and yoke indicated the cause was similar, and it was the first use of medical forensics to actually give that solve an air accident. The other thing that was said was that DeHavilland was working at or beyond the limits of knowledge, but had taken all precautions to prevent failure. Why had the nose section survived 18,000 cycles? The midsection, 16,000. There was no indication in any of the tests they'd done that this was going to happen at 2,000, 3,000 cycles. What transpires and comes out with modern knowledge is that the 2P proof test that they applied to all those two sections probably took the cracks, plastically strained them, formed a strain field around them, and that actually arrested the cracks, probably for 15 to 20,000 cycles, before actually there was enough crack growth to go into base metal outside of that plastically deformed zone that formed a compressive stress around the crack, and prevented further fatigue. And it was purely down to the fact that they did that proof test on the two sections before they did the fatigue test. But there was no requirement by the ARB to do that to every fuselage before it went into service, but that would have extended the life of the fuselage. And it's just because now we can stand here and say that's completely logical, that we understand the science. Back in 1948, 49, that was not the state of the art. So we can look back with hindsight and say, oh yes, we can see what went wrong. There is absolutely no way you picked that up at the time. And Prof Murphy, who was head of school at Birmingham, enough is now known about the fundamental physics of fatigue for engineers to be aware there is still much to be learnt. Donald Rumsfeld, these known unknowns, I mean that's the 1954 version of known unknowns. We now know there's a problem, but we just don't know what it is, or what the physics is. Comet 1 was grounded. Changes were made for pressure having thicker skin around the windows. They altered the shape of the windows so they could redux the windows and get away from riveted joints. Nothing to do with the stress field, everything to do with the method of manufacture. So the Comet windows went round because they could actually redux them in and use this glue technology, which had not failed. And there was a long debate in the course of inquiry about how good the redux joints were. People saying they weren't very good, but all the evidence shows from the accidents that the redux joints held up really well. So that increased the weight, so it was not economic for passenger use. So none of the Comet 1s and 1As flew beyond that. They were used by the Royal Aircraft Establishment for investigations or the RAF for transport, and they basically dropped out of use. Comet 2 was developed at the time, or being developed at the time Comet 3 was developed. That stopped. Any Comet 2s then went into RAF transport use. Comet 3, there was only one aircraft at the time, and so that all stopped. And just to show you, they made the windows round, but nothing to do with the stress field, because Boeing were fine with that. Now, general story of the tragedy was caused by fatigue failure of the airframe. Square windows were the cause of the high stresses. Well, you could argue square windows. I think, given the riveting around a 707 airframe, yes, the skin was thicker, but actually, given the shapes, you'd probably argue that they're still high stresses. So what is it about that that's actually tripped us up? And all of that was reported in the media, and everybody knows square windows. It's a really good story. But what happened next? Well, RE had now got about half a dozen airframes that they could test to destruction. And they did. Fatigue test. Yeah, Robert went for an explosive. How much pressure can we put into a pressure? If we block up all the windows and turn this into a big aluminium tube, how far can we take it before the whole thing explodes? And this was great for the scientists. Because nobody's ever going to fly with no windows and do anyway. But there's lots of reports out at the RAE that looked into fatigue loading, testing, stresses. And they used those comets. Further simulated flights in the tank test were done, and then they turned over the tank test to other airframes. What happens to other aircraft? Can we check out, before an aircraft goes into service, can we go take it down to the RAE, stick it in the tank and make sure that it doesn't fail at 3,000 cycles? And that's what the tank got developed for. Cracks were monitored during the test. Some cracks were stopped, some grew, they're allowed to grow out to catastrophic failure. So there's lots of bits and pieces of data as they just gathered data. And they were trying to learn more and more about airframe fatigue. And they used strain gauges around the cutout. So they did lots of work to understand what was happening, but not much on the fundamentals. And so you've got pages and pages like this, where cracks have grown and you can see number of cycles versus crack length. And so they've done a lot of work on it. Pages and pages of this stuff. And you end up building up this kind of model where you say, well, what's the stress, and where are your strain gauges, and distance out from a window in millimetres against measured stress, and you can plot all this out, and suddenly say, well, you can see where the stress gets quite high, nearly 300 megapascals right by the window, but as you pass through the first and second rivet row, then actually it's going to taper off. What's interesting, I flicked through those screens quite quickly, and also the accident stuff. The failures that were seen were not from that first rivet row closest to the window, they were from the outer one. What tended to happen was that any cracks that formed in the first rivet row either grew into the window and were about that long and therefore stopped, because the window's a big stopper hole, or they grew out to the second row of rivets and stopped, and so the only fatal cracks grew out from the second row of rivets into the rest of the airframe. So actually from a much lower stressed region, we're down in about 100, 125 megapascals at that point. And so actually, interestingly, the fatal cracks weren't in the high stress field anyway. And so the understanding of fatigue developed over the next coming years. It focused everybody's mind scientifically on it. And Paris and Erdogan worked out how to monitor fatigue. And that was their seminal work, 1961, which mapped the stress field and the crack length and the time to failure. And they worked on that. And really, because of the impetus that this accident gave the scientific community, Paris and Erdogan started, a lot of people did the work, but Paris and Erdogan came out with the response to that at that point. And the alloy was no longer used. And so it was kind of, it got us to this place where we now understand fatigue a lot more. And we could use the Paris law to understand that, and this is where I'll whisk through, because this is kind of does more heavyweight maths. We can look at crack, the number of cycles, or the crack growth rate per cycle, and the stress factor in there, and the fracture toughness, how long it needs to grow to. And we could calculate initial crack sizes, aircraft cabin lines, which is what we do today, as a first kind of approximation. But for the aluminium alloy that the Comet was made of, there's no data, really. We didn't test it in that way. It fell out of service, no use. So not tested. So what data do we have? If we want to kind of test that we were right, we've got the fatigue tests on the frames yoke uncle, yoke Robert, and strain gauge data that I've just shown you coming out from the windows, and evidence of cracks on yoke Peter. And we take all that data, which has been published by the RE, although it's a bit difficult to find these days, and we can map it to these, we can look at the strain gauges, and we can start to take the data from the Comet, and we can say fuselage diameter, and this is where I switch to modern units, but you can see the units up there. We can take the data from the Comet, the skin thickness, the stresses, we can plug it all in. We can calculate the hoop stress generated by the cabin pressure loads. We can say there's probably ribs and stringers in there, which will modify it slightly, and we can do certain approximations. And we come out with a stress that's generally higher than the RAE work, but not horrendously so. And that's assuming that the ribs and stringers then take that back down again. 5 cracks grew to failure, so we can roughly calculate a fracture toughness of nearly 50 megapascal meters, and we can plug all this together in those equations. And we can calculate the delta K values. I'm going to whistle through this because this is just Paris and Erdogan stuff. You take the data, you plug it into their equation. I'm not going to, and somebody can come to me at the end and we can go through the maths if you want. I'm not going to spend a long time. But that's all the data that I've managed to glean from all of the reports and plot it onto one graph. And you've got this rough kind of line that goes through there, and if you plot that line through there, you can say how the material behaves. And you do that. And using all this data, plugging it all back in, the material probably behaves slightly worse than a 2000 series alloy, but not markedly so. The initial cracks were probably less than a millimetre in size and difficult to identify on any inspection. And it was probably the case that if we look at all those small crack lengths, they were probably under all the rivet heads. By the time you punched a rivet hole in there and popped the rivet in, you've probably given yourself a millimetre, and you've put the rivet head on top of it, you can't find it. Now, can we quantify that? What evidence have we got today? Science Museum store. That's Yoke Peter. That's the accident Comet from the Elba crash. It was fished out the bottom of the sea, sent to the Royal Aircraft Establishment. They looked at it, kept it for a while, gave it to the Science Museum. The Science Museum now store it, trying to work out what to do with it. That's the taken from the photo. That's the actual crack initiation site. And I was honoured enough to actually get down there. This is a replica, a plastic replica of that surface, made out of plastic, as it is, as I said. And you can see the 2 rivet holes. You can see those pushed through, and you can see if you look under the little flap there, you can see exactly where the crack ran along the edge. There you go. So we will need your glasses for that one. And what you can see is the backing plate that had been attached to the yoke Peter skin, just to kind of hold it for the inspection. But you can see that is the cracked surface running up there. That change in direction is one of the ones that was identified. There's possible striation, so how much it's growing per flight. But given the fact that it spent 6 months in salt water, aluminium doesn't cope well with that. it's probably just corrosion, but you know, if I squint long enough without my glasses on, I could convince myself. But at this end of it, which is more difficult to deny, that top is the bolt hole. And then there's the chamfer in the skin that comes down from that, and the starter crack is sitting under that bolt hole. At the end of the starter crack, the cracks change direction into the direction of maximum stress. So they created this hole, this crack. It sat entirely under the chamfered head. They couldn't see it, but it caused failure. And it's about 1.6 millimetres long when I stuck it on the microscope. So we can find that detail, which wasn't reported in the initial report, but we found it on the stuff ever since. And that sits roughly where it is. Probably the starter crack covers an area of skin in the chamfer, then it changed direction. And the crack changed direction to the direction of maximum stress. As I said, about 1.4 millimetres long before it changed direction, so that's probably the initial starter crack. And we knew that these defects were present because we've seen them before, so we knew that there was likely to be something under every rivet, well, not necessarily under every rivet, but a lot of rivets would have cracks under them. And now you've got a race to the finish. The most the longest crack in the highest stressed area will bring your airframe down first, which is why there was such a scatter. And the ones with the longest cracks, the longest times in service were always likely to be the planes that came out of the sky first. So young Peter, that did that inaugural flight to Joburg, was likely to be the one that caught up because it had been in service the longest. And we know that the crack grew under a doubler plate, so even if they looked at it on that flight, it was under a doubler plate in the skin. So even though it was probably somewhere getting on for about 6 inches long, the chance of actually finding it was slim. And there's a story about 737 and when we're getting on looking at a crack that long and going, I thought the flight crew knew what they were doing. Different accident, but an interesting story. But if we start with the Paris equation again, I'm not going to stop. This is stuff left in because I used it as an undergraduate lecture. We're rearranging all the stuff, integrating, going through, yes. Now, if we just put the values in, we get something that looks like that. And I get a life, just by chucking the numbers in quite crudely, of 1,272 cycles. The stresses aren't quite right. I'm pretty certain of that. And there's a bunch of assumptions in there, but taking the data from that young Peter kind of piece out of the Science Museum, I get that kind of number of flights.
Wow.
Based on no skill on my part, I've come out quite close. I'm quite pleased. But it does show that just by taking the modern understanding of fatigue, understanding the size of your initial defect, you come out with a reasonable life. And if DeHavilland had that knowledge before they started punching rivets, they'd have made some very different decisions, I think. But came out 10 years too late. And so the modern analysis, the failure of pressure cabin was brought about by fatigue. I can't disagree with that. It definitely was a fatigue crack. Manufacturing process of punch riveting rather than drill, rivet and glue, which was where they ended up, caused small cracks, which grew under the repeated loading of the pressure cabin. The bolt hole which failed had defects in the chamfer, which are found, and the interaction between the screen stresses and the manufacturing defects was beyond the scientific knowledge base of that, what they did. And the crack grew actually, out of that bolt hole actually grew both ways. As it got longer, it then developed a crack on the other side, and it just got longer and longer until it was just a critical crack length. Now, critical crack lengths are known in aluminium alloys, and you have kind of plates on the inside of skin now to actually divert cracks to make sure they can't run and run and run down an airframe. And they hit these and divert and go in a different direction, and therefore you end up with a pop flap that opens. Look up Southwest Airlines. And opens up and give a more manageable depressurization that doesn't hazard the airframe. We didn't have those on the Comet, we didn't have the knowledge. Again, we've ended up in a place where the scientific understanding was only just catching up with the reality. Comet 4 flew again. Having fixed all of this, Comet 4 flew. Fewer manufacturing cracks, that's always a good start. First airliner to fly a scheduled service across the Atlantic, 4th of October 1958. Pan Am were about to fly the 707 across the Atlantic. And they went, look, we're going to fly, we're going to be the first company to do this. BOAC snuck in under the wing about two or 3 weeks earlier, much to their disgust, because BOAC didn't make a song and dance about it until about 2 days before, at which point Pan Am was scuppered. That didn't impress the Americans either. So it did that first transatlantic flight, remained in service as the Nimrod 60 years after the Comet first flight. There's an interesting story about how the Nimrod came around. which is probably for another day, but that, yeah, very interesting story about how Nimrod was invented. No, that's the kind of that, but I said there was an Easter egg, and I'll just quickly chip in with an Easter egg. That is, in small print so you can't read it, the list of all the Comet 1s and 1As. The only is 2X prototype, 2 series is in there because they pinched one of the airframes. And you know, you can look it up in books. You've got 6001 through to 6022. So that's your list of Comet 1s and various histories. This bottom one came to Gosford. You look at all the books, 6022 came to Gosford. And you track it through. So that airframe, that's the final Comet 1. Everybody can track it back all the way from the initial Air France registration, VGNZ, in 1953, and you can track it all the way through, 6022. Now, it's not here now, so you can't do this, but if you could, you open up the front door and look down at the plate, and that's a really dodgy photo. Serial number 21. Second line down, EH21. Somewhere, we managed to confuse 2 comets. I don't know where, I can make a guess, but I have no evidence either way. But somewhere, we managed to end up with airframe 21 here. Now you read all the books, and it's 22. There you go. It's not like it's something big and you'd never confuse it, is it? I've got 2, which one was it? I can only assume, and it goes back to possibly the last time that the 2 comets that could swap over and were together were somewhere when the Ministry of Supply was repainting and repurposing them. They had them stripped down, all the paint was stripped off, and they were just 2 bare comets, and they were taking the windows out and fitting round windows in. And it could have been at that point that somebody went, it's that one. That was probably the last time those 2 were actually in the same place without any real registration marks apart from the serial number. But that's the only guess I've got. There you go. Okay. Any questions?
Did they, all this information that they gathered, did they share it with external sources or did they keep it secret?
Royal Aircraft Establishments?
Yeah.
How do I describe what they did? If you worked in the aviation industry, you had free access to all of the REE data. So in my previous life when I worked at Rolls-Royce, I was able to access it, pull stuff out of the library. It was just, you could get as much as you wanted. Now it may be that today it's available. All I would say is it's all on typewritten reports bound up and possibly on site at Farnborough, but I wouldn't like to guess where they are. Whether all these have been digitised, I don't know.
Did it help us to be at the forefront of fatigue testing?
I think it helped, but a lot of this stuff did go to conference amongst the scientific community, so it helped the aviation industry. And DeHavilland's understanding of fatigue, which came along quite quickly at this point because they were learning at the same time as the Royal Aircraft Establishment, they put together and they gave to Boeing for free in exchange for Boeing's data on podded engines. And the argument went that they did not want Boeing to walk into exactly the same problem. Because no company, they didn't want to be accused of, well, you learned, but you didn't tell anybody, and we've just crashed a plane with 100 people on it. They wanted this to get out there to make aviation safer.
What alloy did Boeing use for the first 707?
I have to look that up, but it's going to be an early 2000 series alloy. I just don't know which one. 2014, possibly.
It was not the same.
No, DTD 546 was a UK British designation. It was a British alloy. It was if you had to serialise it now, it would be a 2000 series alloy, but it was never put into that category. It was a UK version of the 2000 series alloy. If I had to make a guess, they were using 2014 aluminium alloy in the States at that time.
Many years ago, when I left this place, I went on a non-destructive testing team which X-rayed the whole of the comets at Waddington. 1970 it was actually.
Yeah.
And it took a whole month to X-ray the whole of the fuselage there.
Yeah.
Just actually templates for each section of the fuselage, and it was an incredible job. But what you did see on the X-ray was quite horrendous, forgetting things like holes and things that, but bits of rivets and things like that that got trapped within the fuselage, and it turned me off flying on a Comet for life. I'd never ever go on one of those.
Okay, but I mean, it's well known that aircraft gain weight during service. They're like people. Every aircraft gains weight during service.
Yeah, yeah. But it's interesting. I think it's the Lower Airlines 737 had a similar situation with the whole top of the fuselage.
The top came off. But she did really well flying that plane in that situation. That was the one where the woman got on and she saw this crack by the door as she got on. And she saw this crack and thought, oh, there's a crack there. Flight crew must know what they're doing. And she just went, what's that one? And when asked after the crack, or after the incident, when they landed, did you see it? Yeah, there's a crack by the door. Thanks. So if you see a crack, just let the flight crew know.
Excuse me for the question, but how much of an issue in the cracks forming do you think was down to the fact that the rivet holes were punched rather than drilled?
That was it.
I mean, it just doesn't happen these days, does it?
There was never an issue because they contributed aircraft through the war, but they didn't last long enough, and they found fatiguing wing structures, so they knew it existed. But so nobody went back and said, oh, you started with a small crack, because they didn't know that was going to be fatal. The idea of punch riveting was effective, known, cheap. Yeah. But they did not know that just by starting base metal, punch it through, oh yeah, it's cracked a bit around the edge, but that crack's only that big. And if the crack grows a bit, you drill a 1/16 of an inch drill through the end of where you think the end is, and you'll be fine. Looking at it today, we're going, no, but trying to look at it with kind of 1947, 1948, 1949 eyes on it, with the knowledge that they had on the day, it's very difficult to criticise the assumptions they made to get to where they were.
Oh, it's fastidious today, the expression drilling and filling in the industry is,
right.
You drill, you take it apart, you clean it, you declare it, you put it all back together, and it's just...
It's a different mentality.
Easily,
but it's this kind of stuff that got us to that place. That place. And without it, we learn more by crashing planes. So.
The French actually used the front of the fuselage in their Caravelle.
Yeah.
They didn't have the same problem. I don't know why that is.
It could have been thicker skin, but they also that bit was Rideau's.
But it was actually the Comet.
Oh, it was a Comet front end, yeah.
Yeah.
Yeah, it was a beautiful aircraft, Caravelle. Yeah, nearly as beautiful as the Comet.
And I just wonder as well with that, how much of it was media representation, especially the way in which the Americans exploited it to push their competition, really.
The Americans were grateful for the information because they avoided that, and then they were able to sell the fact that their aircraft could take more passengers.
Yeah.
Bigger capacity, longer range.
It's like everything in development, isn't it? That it's a new development. You can't refer to books. Or I look at this book of 20 years ago.
Yeah.
It's all new. It's like carbon fibre coming in now, as it were, the last few years. You can't refer to what happened 20 years ago. You have to test and test, look at it, and with the new wings, the carbon fibre. It's all new. You've got to experiment and keep your fingers crossed sometimes.
Yes.
Yeah, you mentioned that the Comet was the first to have hydraulic controls. Does that imply there were servo-assisted controls or simply manual controls hydraulically connected?
Beforehand, or the Comet, sorry.
The Comet.
The Comet was, they basically went to servo control.
They did.
but 4 independent circuits because they realised that you could lose a circuit. More circuits than a DC 10.
Questions at all? Well, thank you, Paul. Fascinating. Your enthusiasm for that subject and the way you put it across and the way you tie together the investigation, the production, the maths at the end of it was fascinating. What amazed me, surprised me, or think is worth repeating is that, or pointing out, is that the jet engine had been designed, developed, been in service for 20 odd years. But it was 1963 before Paris Erdogan worked out the relationship between stress intensity factor and crack growth rate. And yet, you know, there are jet engines around, and you know, all the thermodynamics, all the clever thermodynamics have been done, but that fundamental structure was still waiting to be worked out. I think it was 1961 before they actually drew the line on the graph and said if we take the slope of this curve and use it as an index, use it as a power, then we're going to get something that predicts crack growth rates. But again, it still wasn't until 1963 that they actually published it. A long time after jet engines and all that clever stuff was understood. Really. And the other thing that I want to point out, just repeat, which you made a good point on, if they hadn't treated the original test fuselage differently to the production fuselages, they would have failed the test fuselage, or probably would have failed the test fuselage before the crashes. So, irrespective of whether we knew about the maths and the complexities of crack growth, it was the fact that they overpressurised the test sample that made it better than the flying aircraft that caused the actual failure to be the in-service aircraft. So there's a lesson there. Treat your test sample the way you're going to treat your aeroplane. Treat your aeroplane, or fly what you've tested and test what you're going to fly. And don't have any differences between the two, because you might do something, as Paul said, it was considered to be extra safe to go to that higher pressure. What we didn't know, what the DeHavilland's engineers didn't know at the time, was that they were putting all the stress concentrations into an area of more, that they were effectively insulating the stress concentrations from the effects of the fatigue. And that didn't happen on the flying aircraft. So, fascinating. I've been looking forward to this lecture for months. I'm sure you can understand why. It was fantastic. And I'd like to invite the audience to show their appreciation in the usual way.